Good afternoon, everyone. My name is Pejarat, and I am pursuing my Master in Data Science at Southern Methodist University. Today, I will be sharing my project, Predicting House Price Using Machine Learning. Housing is more than an economic asset. It's central to people's life, community, and long-term financial well-being. Yet, pricing home accurately is challenging because of so many factors interact, such as location, design, condition, market timing, and even buyer sentiment. My goal in this project was to explore whether modern machine learning technique can make house price prediction more accurate and more insightful than traditional economic model. Accurate price prediction matter for everyone in the housing ecosystem. For homeowner, it determines how much equity they hold. For buyer, it affects what they can afford or whether they overpaying. For government, it guides property taxation and planning. When pricing models are inaccurate or biased, it can distort market and lead to inequity, or in the worst case, contribute to crises like we saw in 2008. So this problem isn't just technical, it's social and economic. And that's why bringing data-driven precision to housing prediction is so important. Historically, economists have used what called the hedonic pricing model. It assumes a home value equals the sum of its parts, like size, location, and the number of bedrooms, each contributing linearly. However, in reality, housing markets are nonlinear and context dependent. The same 200 extra square feet might add far more value in urban area than in a rural one. Traditional regression models struggle with this complex interacting effect. That's why we turn to machine learning to uncover patterns and relationships that humans might not explicitly model. Machine learning provides the flexibility traditional models lack. Instead of assuming fixed relationship, machine learning algorithms learn directly from data. They can detect several interactions and adapt as the new data come in. In this study, I compare three models. Linear regression, it is a simple model, interpretable, and it acts as our baseline. Random forest, it is an ensemble of decision trees that capture the nonlinear pattern. XGBoost, a gradient boosting algorithm that fine-tunes prediction interactively for maximum accuracy. My objective was not just to find the best model, but to understand why it performed better. The dataset I use is a mass housing dataset. It is a rich collection of nearly 79 variables, from square foot and material to neighborhood and condition. Data preparation was a crucial step. Missing values were imputed, categorical data was encoded numerically, and numerical feature was standardized for algorithms like linear regression. This pre-processing step ensure that all models learn from clean, consistent data, because even the best algorithm can overcome poor data quality. To ensure a fair and reliable evaluation, I use five-fold cross-validation. Here what that means. The dataset was divided into five parts or fold. Each model trained on four parts and test on the fifth. Repeatedly 5 times so that every data point was tested exactly once. This process helps prevent overfitting and provide a more generalizable measure for performance. I evaluate model using three metrics: OMSE, which penalize large error; MARE, the average prediction error; and R-squared, which measure how much of the variance in price model can explain. These metrics together tell a more complete story about both accuracy and consistency. These are the results averaged across all five folds. Linear regression, our baseline, performed reasonably but left a lot of variance unexplained. Random forest brought a noticeable improvement by capturing nonlinear patterns. Finally, XGBoost delivered the best result, reducing OMSE and MAE while achieving an R-square of about 0.91, meaning it explains 91% of price variability. These show that boosting method can significantly improve predictive accuracy in structured datasets like housing market. Beyond accuracy, one of the most valuable insight machine learning offers is feature importance. Understanding what really drives home value. Across both random forest and XGBoost, the top predictors were overall quality, living area, garage capacity, basement quality, and kitchen quality. What's interesting is that quality and livability outrank factors like lot size or neighborhood, suggesting that buyers today prioritize comfort and interior feature over raw land value. Insight like that can guide both developer and policymaker toward what buyers truly need. These findings have practical implications across multiple domains. Real estate companies can use machine learning based model for automated appraisal. Investors can identify undervalued opportunity, and local government can assess property more fairly. However, we must also consider ethics. If historical data reflect past inequality, the model may unintentionally perpetuate bias, undervaluing certain neighborhood or overvaluing other. That's why transparency and explainability are essential. A model is only valuable if its prediction can be trusted both statistically and socially. In conclusion, XGBoost proved to be the most accurate model, demonstrate how machine learning can outperform traditional methods in capturing complex housing dynamics. But more importantly, it shows how data science can translate numbers into insight by revealing what truly influences value. This model can help build fair, more transparent market. For future work, I plan to include macroeconomic variables like interest rate and apply the model to different cities to test generalizability. I'm also exploring deep learning architecture and fairness metrics to ensure prediction remain both accurate and equitable. Thank you for listening. If you have any question, please feel free to contact me. Thank you.